So what we're going to do is we're going to use our knowledge of quantum mechanics and charges that atoms form to determine the electron configuration of ions. Now, we know that an atom forms an ion by either gaining or losing an electron. And it does this because it fills its valence energy level. Okay? Atoms which lose electrons, we generally refer to them as metals, form a cation and can be monovalent or multivalent. And so the way in which they form their ions might be different. And then atoms which gain, we call anions, and they tend to be nonmetals, and they just fill their valence p orbital. So for example, the formation of my anions. If we look at the electron configuration of my oxygen atom on the left, it has 6 electrons in this valence energy level. It's 2 electrons in the 2s and 4 electrons in the 2p. We know that it will gain 2 electrons to form a stable ion, and these 2 gained electrons will fill their valence p, giving it 8 electrons in the second energy level. So when we want to do the electron configuration of anions, we'd write out the electron configuration for our neutral atom. So for example, we have phosphorus here in our shorthand notation. And we know that it gains 3 electrons, so we'll write out the ion, and then we'll add the 3 electrons to the p orbital to fill it. So anions, we add our electrons to fill our p orbital. Monovalent cations, so these would be my group 1, group 2 aluminum atoms. What they do is we know that they lose electrons from their valence energy level to become a stable ion. Okay, and so we can see here aluminum on the left, it has 2 electrons in its 3s orbital and 1 in its 3p. We know that when it forms a stable ion, it will lose 3 electrons. So it'll first lose the 1 electron in the 3p, since it's slightly larger than the 3s. And the electrons in the 3p are slightly further away from the nucleus, making them accessible first. And then we would lose the electrons from the 3s. So when we're going to do the electron configuration for our monovalent metals, we first write down our electron configuration for our neutral atom. And then we would just remove the appropriate number of electrons. So we know barium, when it forms a stable ion, it will lose 2 electrons. And it's going to lose it from its valence s orbital. And so then we just have to rewrite it correctly in our shorthand notation. Okay. When we look at our multivalent metals, these are often referred to as the transition metals, they can form more than one stable ion. And this ability comes from 3 factors. The first factor is that they always lose it first from their valence energy level. And for every one of them, they all have a valence s orbital. So for example, if I have my iron here, it has the last 8 electrons go into a 4s2 and then a 3d6. Well, the 4s2, it's my highest principal quantum number is 4, so that s orbital is the furthest from the nucleus. So therefore, if it's going to lose any electrons, it'll first lose them from the 4s orbital. And since it only needs to lose 2, and there are 2 there, that's how it forms a stable ion. The second way that we can form a stable ion for my multivalent metals is that I first lose from my valence s orbital, and then I can lose from a partially filled d. So for example, now if I have my iron, we know that iron can form a valence of 3+. So first I would lose from the 4s because it's valence. And then I need to lose 1 more so I could lose it from my 3d, since my d orbital only has 6 and it's not full at 10. Okay, so first I lose from my valence s, and then I lose 1 from the d. And so this would be the electron configuration for iron 3+. The third and final way in which my multivalent metals can form stable ions is through promotion and then losing the valence s. Okay, and so again, this refers to only a small number of them, but for example, copper, we know that copper has a valence of +2 and +1. So, and we saw before +2, we just lose the valence for s. But if we want +1, first we would promote one of the electrons from the valence for s to fill its core 3d. Right? And so now the d is full, has 10. And then I'm going to lose the one electron that remains in the valence s orbital. So we have this electron configuration. So finally, to wrap up, multivalence is due to the loss of the electrons from the valence energy level, which is for all of my transition metals or metals that can be multivalent that are in the middle of the periodic table. They're going to be s orbital electrons. Then I can lose from my valence s, and then I can lose from a partially filled d. And usually we lose from a partially filled d to make it half empty or to empty it. So for example, chromium 6+, it's 6+ because I lost the 2 in the valence s orbital, and then I lose the 4 that are in the d orbital, and it empties the d orbital. The third and final way in which we get multivalence is that I would promote a valence s orbital to fill a core d, and then I lose the electron that remains behind.